Alright, in this video I'm going to try and replicate what Luke is doing in regards to his work on the motor, and that is creating a flyback voltage from the rotor coils inside the motor. This motor here is a 24 volt DC motor. That bit there you're looking at with the cutaway cases and the coil is just another little experiment I've been carrying out. Disconnected at the moment, but yeah, what we're going to be looking at is finding these inductive kickbacks coming from the brushes when the rotor segments switch. This is actually a rotor out of a motor of the very same. I have about 4 of these from old electric scooters that no longer work, and as you can see we have our rotor segments. They're a fairly high quality motor, in that they're fairly robust in the way they're built. Very neat windings. You can see it's much better than a Chinese throw together job, which looks more like one of these messes here with crap everywhere. So what I've done here, because my scope and my power supply run a common ground, the diode is coming off the positive, but it'll be collecting only the inductive kickback on the negative side. So normally we would have the diode on the negative side to collect the forward or the positive voltage current through that diode, but this way we're doing it back to front so as I can put my scope grounds on the same clip lead as my power supply. The reason I'm not using my inverter anymore is because I blew it up. I didn't like our little motor project from before. So we're back to sharing common ground in my scope until I fix my inverter. So that's what we've done. So what I've actually done, because the probe is here on the negative side coming from the positive terminal, and the ground is what would be the positive side of the inductive kickback, and we simply invert channel 2. But I also have a diode in series with our positive input to stop any U-boot high voltage pulses of some description going back to my power supply over here, which toasted it last time. Okay, so it's just our current meter, nothing too important. We're just looking for these inductive kickback spikes from our brushes. Now it's good that I have the hole here because I can see the brushes actually arcing a very small amount in there, but not a lot, because they're a fairly high quality motor. So just go hold that with my arm and turn it on. The yellow trace on our scope is just across the motor itself. So on our blue trace, which is searching for these inductive kickback spikes, we're set on 500 millivolts per division. Excuse me. And 5 volts per division on our yellow trace, which is across our motor. And you can see that we do indeed have our 12 volts, which we're delivering from our power supply. And here we can see absolutely no inductive kickback spikes from brush noise whatsoever, not even 500 millivolts. So I'm going to turn the motor up to 24 volts, that's what it's rated for. Okay, so now 24 volts, 300 odd milliamps. We'll have to drop the voltage divisions down again, 10 volts per division, so you can see we have our 24 volts. What I can see there is a dip in voltage every time the brush comes in contact with the next segment. But once again here, this inductive kickback line is very, very quiet. Not even 500 millivolt spikes there. I'm going to change the scope so we can detect the peaks. Now we can see some noise on the brushes. But I am at 500 millivolts per division and 1 millisecond samples, and our inductive kickback is not even exceeding 500 millivolts. Occasionally one might hit it, but not very often. So very quiet across the brushes. Probably can't see that, but I can see, well, there's not very much arcing in there at all, because on the brushes, because like I said, these motors are fairly high quality. But what we're going to do next, so I'm going to put my pulse modulator in the whole shebang here, and we're going to have another look when we actually pulse the motor itself at different frequencies. So we'll be back shortly.